All right, it's time to get started. Welcome back. I hope you are having a good day. We have homework due tomorrow, as usual, and we also have our next test on Friday. So I think you know what to expect at this point, but the test will cover everything up through, well, I might as well include a question about what we do today. So if you are following along on your checklist, maybe I'll just tell you what in my opinion, the new topics on the test. The new test topics shall be the Bonshoff was the first one. B3, that's the Bonshoff. And then we had the C1, C2, C3, C4, and C5. So this was, these are all about gerrymandering, but the C1 is determine the possible outcomes. This was on the homework last week. C2 was draw districts to achieve various outcomes. C3 is the convex hull ratio. No, the efficiency gap. I skipped one. We did that last time. Efficiency gap. And then the convex hull ratio, which we started talking about last time, but are going to get to the good stuff today. And then also the last of our geometric measures is the isoperimetric quotient, which we are going to talk about today. So you probably won't be an expert on the isoperimetric quotient, but I will put a question on the test. Once you know how to do it, it's not so hard. That's what we're going to talk about today. Anybody have any general questions about the test? Of course, the test, as usual, will also include questions on all of our previous topics, but you are not going to do all of the questions. And you can, bring your checklist with you, but you will not use any other notes or anything. And that includes not using a calculator. For the efficiency gap on the homework, I typically would expect you to write your answer as percentages, but you can just write a fraction. Any other questions about the test? All right, let me know if something comes up. I would be happy to chat about old topics if you have old stuff that you're still not clear on. Let me know and we can talk about it. I got time on Wednesday and Thursday. All right, great. Let's continue. Oh, sorry. Actually, before we continue talking about the convex hull ratio, I had a little math current events to share with you. I don't know if you've been following the math news lately. There was a major discovery discovered last week, or it was first announced last week, on the topic of aperiodic tilings. Anybody into aperiodic tilings? This was something that there was an article in the New York Times about it this weekend, so it got some press. I will show you a picture. Whoa, sorry, I didn't want camera. I want photo library. Here's a picture of an aperiodic tiling which was discovered. This is actually something that people have been working to discover since the 1970s, but finally somebody figured out how to do it. This is called an aperiodic tiling by one shape. So this kind of blue shape that looks sort of like a t-shirt. All of these other ones are just another copy of that same shape, which has either been rotated or mirror image reflected. What's interesting about this is you can continue this kind of pattern to fill out the entire flat plane. You could tile your bathroom with tiles of this shape, but this is called an aperiodic tiling because actually they demonstrated that this pattern, actually it's not really a pattern. This tiling, if you use that shape and fill out the plane, it never repeats. That's what aperiodic means. Actually, there are no repeating patterns in this arrangement of the shapes. That's why it's called aperiodic. Periodic means something which repeats itself after a certain amount of time. Aperiodic means that never happens. So this is something that people have been searching for a long time to find a way to do that, but only discovered, they just announced it last week, so discovered very recently. Fun times. You can, print yourself out some of these shapes and put them all over your wall or something. They will fill up your wall, but they have no repeating patterns in order to do it. Any thoughts about that? It's kind of cute. My mom called me this weekend. I said, hey, Mom, you heard about the new aperiodic tiling? She had not, but now she knows about it. My mom was a math major when she was in college, so she's vaguely interested, but she's also a quilter. This is big news to the quilters out there, because now you can make a kind of weird non-repeating pattern with only one shape, which was not possible, or it was not known how to do this before. All right, fun times. Tell all your friends about the new aperiodic. This particular shape is called the aperiodic monotile. That is, it's one shape that can tile the plane aperiodically. Very interesting. Anyway, let's continue talking about the convex hull ratio, and then we're also going to talk about the isoperimetric quotient. That was that last thing on the list of topics that I said there. The convex hull ratio. First of all, I hope you remember what the convex hull is. So that's like you begin with one shape, and then from that shape you can create the convex hull, which is typically a slightly larger shape, and it is the shape which is obtained by filling in all of the kind of inward protrusions in your shape. Another way of thinking about that is if you wrapped a rubber band around this shape, where would the new boundaries be? That's called the convex hull. So this is my original shape. If I were to draw in the convex hull, you get the convex hull by connecting with straight lines to fill in areas like this. And also there's one over here that I need to fill in. I believe other than that, there are no sort of inward bumps. And so this whole shape now is the convex hull. All right, the original shape was smaller. This is called the convex hull. All right. And we had, several examples from last time. And what I was trying to impress on you was if you have a fairly ordinary looking shape like this maybe, that shape, its convex hull, involves adding in this part and also this part. And maybe something over here, maybe a little something there, a little bit right there, maybe. Anyway, you fill in all of the inward bumps. So that is a shape which is pretty close to the convex hull. Like the original shape is not all that different from the convex hull of that shape. But if you have some kind of long, wiggly, wormy shape, like this maybe, then this shape, sorry, I went off the map. This shape here actually is quite different from the convex hull. If I do the convex hull of this squirmy, wormy shape, I have to add in all of this area here.
Looking at it makes me want to vomit.
Sorry.
No, it's okay.
I'm being edgy today. This one, you got to fill in all of this too. All right. Sorry about that.
No,
I think it looks kind of like one of those like little toddler cars, the yellow one with like the red roof on it. You know that one I'm talking about? Anyway, this crazy shape here, this wormy shape is very different from the convex hull. Like the convex hull shape, at least by area, the convex hull shape, the red region, is much bigger than what I started with. So the moral of the story here is a quote-unquote normal shape is similar to its own convex hull. All right, CH for convex hull. That's like the one on the left. When I did the convex hull, it wasn't all that different from what I started with. But a weird wormy shape has a convex hull much bigger than the original shape, the OG shape. Everybody knows what OG. The convex hull. Yeah. Yes.
Oh, so is there a way to determine when you fill in the whole thing versus only, I guess, the part where you're filling it? Like,
Yeah, I suppose. You mean here why I scribbled the whole thing?
Yeah.
Yeah, I think this is just me being inconsistent. So the convex hull is equal to the entire shape, including what you started with, plus all the extra little bits. Yeah, so technically if I were to draw in the entire convex hull, I would also, scribble the entire inside. And here, the entire inside of this is the convex hull. Yeah, sorry if that wasn't clear before. All right. So here, by area, certainly this convex hull is very large, even though what we started with by area was not all that large to begin with. All right. So a normal shape is similar to its own convex hull, but a weird wormy shape has the convex hull much bigger than the original shape. This says OG shape. What I mean by bigger is by area, right? The area of the convex hull shape is a lot bigger than the area of the original shape when it's a weird wormy thing, all right? And so this is how you define the measurement of how weird the shape is in terms of those areas. And it's called the convex hull ratio. So that's a clue that you're going to make a ratio, a fraction. So the convex hull ratio I'm going to write CHR usually, convex hull ratio, is, it's just a simple formula here. It's the area of the original shape divided by the area of the convex hull shape. All right, and that's all there is to it. That's what the convex hull ratio is. And the area, I will have you notice, the area of the convex hull is always a little bit bigger, or perhaps the same, right? The convex hull makes it slightly bigger than what you started with. But for a nice shape, if the shape is nice, the OG area is almost the same as the convex hull area. For a nice shape, that's true. The original shape's area is pretty much the same as the convex hull shape area. And what that means is this is a fraction in which the top and the bottom are basically the same, which means this value will be close to 1. All right? We typically write this as a percentage. And so in this case, if the shape is nice, this fraction's value will be close to 1. That is to say 100%.
How are we then writing that in an exam?
I would just leave it as a fraction.
But like with percentages?
No. We're gonna do a bunch of examples. Okay. I think you'll see. But yeah, I mean, it's typically described as a percentage, but you won't be able to find the percentage unless you have a calculator, which I won't ask you to do. So you would just write it as a fraction. But anyway, if the shape is nice, our original area is almost the same as the convex hull area. So the convex hull ratio is, I will say, close to 1. That is to say 100% for a nice shape. All right, because the numerator and the denominator will be basically the same value. Whereas if the shape is a squirmy, wormy shape, so for a weird shape, remember that crazy shape that I drew before? The area of the convex hull will be much bigger than the original area. So for a weird shape, the denominator, well, I'll say the CH area is much bigger. So in this fraction here, the denominator is much bigger than the numerator, which means the fraction value will be close to 0, or as a percentage, 0%. So for a weird shape, the convex hull area is much bigger, so the convex hull ratio will be close to 0. All right? And so in this way, this fraction here, the convex hull ratio, it gives you a measurement between 0 and 1, or from between 0% and 100%, which just tells you how weird the shape is. And close to 1 is like better, close to 0 is like worse. All right? this is how the convex hull ratio works. So the convex hull ratio is like, you could think of it as like a score for how weird the shape is. Where 0 is very weird and 1 is not weird at all. That's the idea. This is the whole purpose of the convex hull ratio. Remember, you use this in the context of gerrymandering to measure, just looking at a shape, how strange it is. You can measure this in this way. All right? I would like to do some examples. When you think about doing examples, you immediately run across a serious problem, and that is, for example, I'll just make something up here. How about this is a picture of my hand with the appropriate number of fingers on it. What is the convex hull ratio of this? So the convex hull ratio is the area, it's the original shape area divided by the convex hull area. And like I said, you arrive at an immediate problem if you actually want to figure out what the answer is. Can anybody say what's the problem with figuring out this fraction here? Yeah.
Finding the original area is going to be very difficult.
Yeah. How can you find the original area? Does anybody happen to know like a geometry formula for the area of that thing? The answer is no. There is no such geometry formula. Maybe you remember how to find the area of like a triangle and a circle, but I mean, there aren't formulas for other kinds of shapes. So finding the areas is in general, difficult thing to do for a weird shape. Finding an area of a weird shape is hard, right? I don't know if you ever thought about this, like, when you're a kid, you learn that if you want to find the length of something, you use a ruler, right? What do you use if you want to find the area of something? Anybody know? A what?
Formula?
A mathematical formula. Okay, but what if the area of the thing is not a triangle or something like that? The answer is, I don't know. There isn't like a thing like a ruler that you can hold in your hand, which is used for measuring area. A ruler is used for measuring distances. There is, though, an old school and very simple sort of instrument that you can use to measure the area of things. And I have a delightful handout about this. It's a very simple idea. In my opinion, this could be something that we teach kids about when we teach them how to measure lengths. We could also have them measure areas. It's something called the dot planimeter, which I would love to share with you. Tell your friends about the dot planimeter. This didn't really have to be a handout, but there's a lot of pictures. Rather than making you copy the pictures, I thought it'd be easier to just hand it out. So I'm going to put this on my screen. Come on. No. So the dot planimeter, what it is, as an instrument, this was people don't really use this today because we have computers that can do things a little bit nicer than using dot planimeter. But the idea is it would typically be just a bunch of dots printed on a transparent sheet, and you lay the transparent sheet over whatever you're trying to measure the area of, and the dots are equally spaced, of course. And so the dots, you can imagine they are lying inside of squares that are like 1 square centimeter or whatever, 1 square inch if you prefer. And then all you got to do to find the area of this thing is to count up the dots that are inside of this thing. All right, that's how the dot planimeter works. It's a very, very simple idea, but it actually works fairly well. So if you want to know the area of this shape, you lay down the dots on top of it, and then you just count how many dots are on the inside. you're basically counting this area, which is not exactly the same as the area of the heart shape, but it's pretty close. It's just off by a little bit around the edges. In real life, if you really had to do this super accurately, the way that you would do it would be lay this down and count the dots, and then pick it up again and lay it down just at a random angle or something like that and count up the dots again. If you do it a few times and then take the average of your different measurements, you actually can get a very accurate answer for the true area of the shape. All right. When it comes to like actual sort of instruments for measuring areas in real life, this is about the most simple way that there is to do that. All right. Counting the dots. One thing that comes up, and you can see on the bottom of your paper there, what if the dot is on the line? This is something that is always going to come up every so often. One of the dots, like this dot right here, is right on the line. Should I count it or not? Well, it looks like when I was doing this, I didn't count it. I judged that that was like slightly outside of the line. So technically speaking, if the dot is on the line, what that means is basically the shape is sort of half in and half out of this little rectangle, which means kind of like the mathematically appropriate thing would be to count the dot as a half. Stop. All right. If you see a dot that's on the line, that sort of counts as a half, but it's annoying while you're counting the dots to keep track of halves while you're going. And so instead of keeping track of halves, here's a slightly fancier setup. You make your dots so that half of them look different. And then it says if the dot is, so first of all, if the dot isn't on the line, that is it's totally inside, then you definitely count it. If the dot is on the line, you're going to count half of them and not the other half. And the way this works is if it's one of these sort of empty dots on the line, you count it. If it's one of these dot inside of a thing and it's on the line, you don't count it. All right. So this is how you use the dots, and you count the ones, all the ones on the inside you count, and the ones that are on the edge, you count them if they are this kind, and you don't count them if they're this kind. Or you do the other way around. As long as you're consistent, it doesn't really matter. All right? This is called the dot planimeter. And you can use this to measure the area. So if I were measuring the area of this thing, we can all do this together. This is slightly annoying, but it's easy to do. I am going to count the dots, and the ones with the sort of empty ones, they count if they're on the line. But the filled in ones, they do not count if they're on the line. So when I go across here and count, you can mark this off with your pencil or something. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to say that's not quite on the line. This one right here is either on the line or outside, so I'm not going to count it. I said 11, right? 12, 13, 14, 15. That one looks like outside to me. There's a certain amount of eyeballing that you have to do here. I lost my count. Is that 15? And then this one's on the line, so I don't count it. 16, 17, that one's outside. That one's on the line. I'll count that one. 18. I got 18. All right, 18 dots means that this shape is area 18 square whatever. So I don't really care about the units. I just care about the area. The reason I don't care about the units is because when you do the convex hull ratio, you're dividing two areas by each other, and then it doesn't matter what the units are. All right, this is how you measure the area of something if it has the dots on it. Yeah.
So, like on the test, are you gonna have it like this example, like with the dots already in it?
Yeah, that's right. So in people using dot planimeters in real life, we'll have a transparent one that you can just lay on different things. Rather than that, I thought about handing these out and then say, remember your dot planimeter, bring it to the test. I think it's easier. I will just print out the dots on the picture already for you. Yeah.
An issue that I have with this is that you could just shift the heart around on the grid without changing the size or area, and the dots are so far apart that the number of dots it hits and the kinds of dots it would hit would be different.
Yeah, that's right. So it is a fact that this number of 18 is not entirely accurate to the true area, of course, is probably not a whole number anyway, right? But yeah, what he said, you could actually get a different answer if you move the grid slightly. I think that's what he's saying. And so the answer that I got is actually specifically for this positioning of the grid, which doesn't quite represent the true area. Like I said before, the way that this would typically use, if you really want high accuracy, you would reposition the grid several times, make the count every time, and then take the average of all the measurements so that those differences between grid positionings would kind of even out. Because it is true that repositioning the grid will give you a different answer, although it can't give you a totally different answer. Like there's no way to move the grid here to make it so that you get 0, right? Like it's always going to be about 18 in this example. And if you do it a lot of times and take the average, you get something that's very, very close to the true area. So this is not super accurate, but it's pretty good. And if you want to make it accurate, you do it many times, which we're not going to bother doing that. All right. Anyway, this is using the dots to find the area. So now we can actually do some real examples. And I thought I have another handout here, because this will always involve me giving you a picture of a weird shape and then you doing the various areas to find the convex hull ratio. So what I have here are the 5 different Connecticut congressional districts. And I would like to find the convex hull ratio for each of them. Maybe I'll do a couple of them and then you guys can, I will let you guys try the rest. This does involve counting some dots, which I know is a bit annoying and can drive you crazy if you do it for hours at a time. I'm not going to make you do it for hours at a time. All right. I hope nobody has that oh, this picture is messed up. Is yours like that? No, the dots, I copied the wrong dots. These are all the same dot. Sorry. I hope I have a better version of this picture. This is so embarrassing. I was glancing at my pictures and I grabbed the wrong one. Can you give me a moment?
Could you do gerrymandering with this point system? Like its own type of gerrymandering? Like as opposed to reshaping districts, you just move where you want the grid to be?
I'm not sure. Moving the grid can give you different answers, but not wildly different answers. They're still going to be more or less the same. So I'm not sure. All right, this is the one I want. I'm almost there. All right. So I don't want that. What? Where is it? Oh, that's the wrong one again. Do it. Okay. This is going to be so worth it. All right, there it is. Sorry for all of that. So let's try district number 1. Remember, we have to count up the area of the original shape. It's the numerator of the fraction divided by the area of the convex hull. So when I'm counting my original shape, maybe I'll count those with, I'm going to make little marks as I count the dots. Maybe I'll mark off the original dots with a blue. So remember the way to count them. If it's on the line, like this guy here is on the line, I count it, that shape. The dot with the filled in inside, you do not count it if it's on the line. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. And those three on the bottom are on the line, so I'm not going to count them. So I got 27 dots inside the original shape. Now, as you're counting, you might make a eyeball judgment that's slightly different from mine about what's on the line and what's not. I don't care about any of that. If you're like slightly close, that's fine with me. If you said, so what did I say, 28? So for number 1, I have the convex, or the original shape is 28. Now I have to count up the convex hull area. So for that, I'm going to, first of all, draw in the convex hull. Don't like this picture here. Now, to get the convex hull of this shape, you have to add in, like fill in all of the inward intrusions. That would be something like, I don't know what's going on here. This Notability does not like it when you draw on top of a picture. All right, I am trying to fill in the convex hull. Remember, you do this by drawing straight lines to fill in all the little itty-bitty inny regions, like so. All right, I believe that is now the convex hull. And now I count all the dots which lie inside the red boundary. Now this automatically includes all the ones I already counted, so maybe I'll just start from where I counted before, which is 28, and I'm going to add on to that. So maybe the new ones I'll mark in red. So I'm going to start counting from 28. I go 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42. 42 is what I get. Those three guys on the bottom, they were on the line, but they're actually totally inside now, the red area. So 32 is what I got from that one. So this is 28, and the convex hull area is 32. And so my sort of final answer for that, the convex hull ratio here, would be 28 divided by 32. Whatever that is. So on a test, I would expect you to just leave it that way. If you like, you can divide it, and you'll get a percentage. Yeah.
Go to the left of the picture again.
Yeah, sorry. It's hard
Why
to.
is it just 32?
You've got more than 32?
You have all the insides of the reds?
Yeah. I think I counted all.
Isn't that
You only
28
added
and on
40.
top?
42.
Oh, 42.
Yeah.
Yeah, what?
Yeah.
Yeah. Okay, thank you. Yes, it's not 32. That's only 4 extra. It should have been 42? Great. Sorry about that. I'm distracted by by my technical difficulties. My arithmetical difficulties. 42. Thank you for that. All right. Any thoughts about that? Let's try district number 2, and then I will have you all try to do the other ones. So when I do district number 2, again, I'm going to start by counting the ones that are on the inside. These guys across the top are all on the line, and they are not the kind that counts on the line. I will begin with this one here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. I got 32, not 42. I think that's right. So for district number 2, my original area is 32. And then the convex hull area is For this one, I have to fill in. It's actually not all that much more in this example. Actually, I think we've got to go all the way from here up to the top. Remember to fill these in using straight lines, like so. All right, I think that's the convex hull region. So I had 32 to begin with, and I now count some more. I now go 33, 34, 35, 36, 37, 38, and I think that's it. All right, so the convex hull area is 38.
Does that point? Does that point on the red? Like, does that count as being on the line?
This guy here?
Yeah.
I would say yes. Does it look like it's slightly outside the line to you? I think it's on the line.
Sure.
Yeah, I mean, if there are going to be times when it's a little debatable, and then make your best judgment. And I will expect, when you're doing these questions on the test, I will do my answers. I will expect your numbers to be within 1 or 2 of what I said. If it's way off, then I will be concerned. But if it's more or less the same, then that's fine. All right. So my final answer here would be the convex hull ratio is 32 divided by 38. And in terms of the percentages, you can compare one to the other, right? So if you actually have a calculator, I'm using my my little phone calculator here. If I do 28 divided by 42, I get this is 0.66, that is to say 66%. Remember, 100% is really good, 0 is really bad. Like 0 would be a very weird shape, 100% would be a very nice shape. Whereas, so that's 66%, the other one is 32 divided by 38, which is 84%. And so the second, District 2, in terms of its geometry, is a nicer shape than District 1, which, I mean, I could have told you that to begin with. District 1 is a very weird looking thing. District 2 is more like a rectangle, all right? But the point of all this is that this is a specific measurement that you can use to, statistically say how weird the shape is. All right? I would like you to see how you like the other one. See if you can do this for the other ones. If you get tired of counting dots, then you can stop, I suppose. But I want to just make sure that everybody knows how this is going. And I will walk around and see how everybody's doing. Here we also have the entire state of Connecticut, which is another interesting example you can do.
I'm just wondering, the correct way, would it be just like draw a straight line from here? If I was more specific, I could go like this.
Yeah, that's too small. You have to go straight across.
Oh, I see.
Because what you drew here is still in your place.
Oh, right. Okay.
If you imagine wrapping a rubber band around it, like a rubber band wouldn't do that.
I see. Okay.
This is not the right shape that you want. It has to be straight lines that sort of plug in close to the shape. The way to imagine it is you imagine you wrap the rubber band around this shape. That's what you wouldn't do that. It should come straight across the house.
Do you aim to include the dots when you do that? Or no?
No, the dots either will be included or not, but yeah, like straight lines across.
So, as long as you put that down in the center circle on the line, you don't count it? Okay, so, like, even if it's barely touching.
Yeah, I don't know. I mean, I like it. This one, I definitely not.
Yeah, what about like that one though?
Yeah, that's a little debatable. I'd probably say that's on the line. It's up to you. Like I said, if you're like 1 or 2 different, you know how to do that. like they're not on the line of the
Yeah.
compass.
Oh, okay.
Figure out how.
All right.
Yeah.
Not.
Can I say this? I don't think it is actually
You just do like these
still.
Yeah.
straight lines, like
And sorry, and another thing, when I do this and in this again lines,
Yeah,
I don't.
like-
Yeah, I don't care about that. That's
so
just
basically what.
And when I have to do this in the exam, do you want us to like do this or the okay?
Okay.
Like for five.
Just based off the sheet, is that more just because the sheet is regular or
Yeah, I think-
almost like it's not 100% reliable the system, but
Yeah, I would say it's because so much of the area
it is in
right on the
it's just to get over to 65.
yeah, so it's not
You
always
just draw straight
like
lines from
if the shape was if it was a Convex measure, this would then this would be short.
Oh,
I see.
like
Another.
that.
Okay.
What about you think that is like is it already
The other shape, yeah, it would involve learning to, it's kind of like if you imagine wrapping a rubber band around your shape. It's like a shift or which would include like those kind of like shapes. Just like that water shape. You guys all right?
I know you're talking about. I know you're talking about.
like that. So
Like, maybe what is around like, let's say, usually if it's just very touchy, it's the and I think one little comment is across the top.
I was.
Okay.
I do.
Like that middle part.
Yeah.
Is like that. Well. Supposed to be like that.
Okay.
Yeah, I think he has some questions. I like this one.
Yeah, like to me, I would count this as.
Okay. And like even like that one.
That one I would say is.
Okay.
Can I say something about this?
Yeah. There's a lot.
Guys, actually, this is.
Yeah. Okay, thank you.
All right. All right, can we talk about these? I think as I'm going around, it seems like people are doing fine and either, already done or driving themselves crazy by counting all the dots. It is a little, it can make you crazy if you do this for too long. Actually, there were instruments invented in the old days, like electronic things, to count the dots for you, which are fairly sophisticated and didn't work very well. Of course, nowadays with computers, people don't do it this way anyway. There are actually, you can get. I happen to know because I have a strange interest in these things. There are people who study trees, like health of trees. One basic thing that they use to measure how healthy a tree is the area of the leaves. And so there are people who have to like go out in the woods, get a bunch of leaves and measure their areas. And there's actually a handheld device for doing this, which looks kind of like a hair flattening iron. It has it's like this kind of thing. And you do that and you wave it, you sort of clamp it on your leaf and you drag it across the leaf, and it has some kind of a scanner in it. And it tells you the area of the leaf, which is pretty cute, I think. I don't have one of those because they're very expensive. But If you ever see a cheap one, I'm interested because I think it's a cool idea. Anyway, can I just, let's just look at, say, number 3. It is important, you know, everybody can get slightly different counts when you're deciding what's on the line or what's not, but it is important to draw the convex hull properly. And I hope you remember thinking about what the convex hull is exactly. It's like what you would get if you wrapped a rubber band around the shape. So for instance, along the bottom, you have to connect all the way across the bottom like that. I saw some people trying to connect up like this or something, but that's not good enough. You're going to miss some dots if you go in close to the shape like that, but it should not. The convex hull should have no inward bends to it. So it really has to go straight across there, and then also something like this, straight across there, a little something like that, a little something like this. Really more so than counting the dots slightly differently, something that can really mess up your answer is if you draw the convex hull improperly. Then you will really get a wrong count of the dots. All right, so that's what the convex hull is. I will just say what I got. I counted these up ahead of time. So for number 3, I got my convex hull ratio was 20/31. So if you got something close to that, then you know on the test I would mark this right if you're vaguely close to that. If you were way off, then you may be doing something wrong. So for the entire state of Connecticut, I got 44/50. For number 5, I got 52/70. And for number 4, I got 36/49. Anybody feel like any of those are way off? You probably didn't get exactly the same numbers, but I hope that you got something close to that. All right. Excellent. So that's the convex hull ratio, and I don't think we really need to say much more about the convex hull ratio. It's not so hard to do. It's, I suppose, a little annoying to count all the dots, but there's not a lot to it. All right. We have about 30 minutes remaining, and I think that is enough time to discuss our last measurement of gerrymandering, and that's with the more sophisticated name. This is called the isoperimetric quotient. The isoperimetric quotient. And this is a different sort of measurement of how weird the shape is. This is a different, you could think of as like a score for weird shapes. And it is interpreted in the same way as the convex hull ratio in the sense that isoperimetric quotient, I'm going to write as IQ. IQ close to 0 is bad, and the isoperimetric quotient close to 1, or 100% if you prefer, is good. All right, but it's measured differently from the convex hull ratio, and you will, if you have the same shape and you measure it in these 2 different ways, you will get 2 different answers. They're just 2 different ways of thinking about what it means for a shape to be nice. All right, so I will. I'm gonna draw again sort of a fairly nice shape versus a weird shape. Hopefully this won't be upsetting to anybody. Let's say that's my weird shape over here. All right, this is weird. Now, the isoperimetric quotient, the idea behind this has nothing to do with the convex hull. So we're not going to even think about the convex hull. It has to do with the area of the original shape versus the perimeter of the original shape. Remember, the perimeter is the distance around the edge, all right? And what I would like to notice here is a nice shape has can I just say it like this? The perimeter is not so big. Whereas in my weird shape, actually this is not much area than the one on the left. Not much more area than the one on the left, but it has much, much more perimeter. All right? I feel like the shape on the right-hand side has a lot of perimeter for not so much area. Okay? That's the defining feature when you're measuring the isoperimetric quotient, is how much perimeter is there versus how much area is there. All right, so the weird shape I would describe as big perimeter, not much area. And that's what the isoperimetric quotient is supposed to measure. You can like the word in there has the word perimeter as inside of it. So the isoperimetric quotient measures the area versus the perimeter. All right. If there's a lot of perimeter, then it's a weird shape. If there's not so much perimeter, then it's not a weird shape. That's the very basic idea behind the isoperimetric quotient. And it's basically, how you do it is basically just area divided by the perimeter. So if the perimeter is really big, then this will be close to 0. And if the perimeter is not so big, then this will be closer to 1. That's the basic idea here. I say it is basically A divided by P, but that is not quite what it is. So it's basically A divided by P, but with some, some extra pizzazz. It's not just A divided by P. It turns out A divided by P is not actually good enough to measure properly. So I will say, but with some modifications. All right, for example, I want to try to explain what's wrong with doing just area divided by perimeter. If I have just like a square, say, which has distance 1 on each side, here the area is 1. The perimeter, anybody, any masters of geometry out there? What's the perimeter of that?
4.
It is 4, yeah. That perimeter means the distance around the outside. So the perimeter here would be 4. So in this case, the area divided by the perimeter is 1/4, right? But what if I had another square that was the same shape, only bigger, all right? This is just like you scale the shape up. Let's say this is now 10 on each side. In this case, the area is 100. That's because the area of a square or the area of a rectangle, you multiply the width times the height. This would be 10 times 10, which is 100. The perimeter, what's the perimeter here? 40, yeah. So if you do A over P this time, you get 100 over 40, which is actually 10 over 4. That's 2.5. These are quite different, aren't they? This 1/4 here versus this one. Even though they're the same shape, this is the problem. They are the same shape. Now this is a bigger square than that one, but this is supposed to be a measurement of how weird the shape is, not how big the shape is, right? Here they are the same shape, but they're giving me different answers from the one to the next. So the moral of the story is you can't just use area divided by perimeter. And really the problem is because these two things, the area and the perimeter, are different sorts of measurements. Like in terms of the units, the area is an area, but the perimeter is a distance. If you like, the area is sort of like a two-dimensional thing, but the perimeter is only a one-dimensional thing. And it doesn't really make sense to divide them in this way. It turns out the simple way to resolve this is instead use A divided by P squared. And this actually fixes all of these problems about the fact that the area is a two-dimensional thing while the perimeter is only a one-dimensional thing. It turns out if you square the perimeter, then everything works great. That is to say, you will get the same answer for the same shape. So if we do it that way, I'm just going to quickly say, what do we get for the area and the perimeter here? Again, this time the perimeter is 4, so P squared is 16, so A over P squared is 1 over 16, right? Versus the one that was 10 by 10. Here the area is still 100. Here the perimeter is now 40. So P squared is 1600, and then A over P squared is 100 over 1600, which when you reduce the fraction, sorry, not 1,000, 100. When you reduce the fraction is 1 over 16. What I'm saying is, just by squaring the P, it makes everything work great. So now I have the same shape both times, actually gives me the same answer for this quotient both times. a square, you're always going to get 1 over 16. All right? So a over p squared is the formula. Unfortunately, there's one little extra pizzazz, which is especially spicy. The true formula, the isoperimetric quotient is 4 pi a over p squared. This is kind of annoying, but the way that they do this in real life is by multiplying by 4 pi. What's the purpose of the 4 pi? If you multiply by 4 pi, it makes it so that a circle always has isoperimetric quotient equal to 1. If you work out the relationship between the area versus the perimeter of a circle, it turns out if you insert a 4 pi in there, it makes it so that a circle has area 1. I think I told you on the first day of class that this class does not involve a lot of memorizing of formulas. I said there is one formula that I'm going to ask you to memorize, and that's this. It's slightly weird, but not extremely weird. When you're doing this on a test, I can tell you're already wondering, how am I ever going to do this formula on a test without a calculator? The answer is, I would expect you to just leave it like this without actually multiplying by the pi. We're going to do some examples. You'll see what I mean. So this is the formula for the isoperimetric quotient. I will just say the 4 pi is so that IQ of a circle is 1. All right? So in terms of the isoperimetric quotient, so I will say according to isoperimetric quotient, the best possible shape is a circle, right? That formula up there was specifically invented so that you get 1 if you are doing this to a circle. So in terms of the isoperimetric quotient, the best possible shape is a circle. Even something like a rectangle will be less than 1. But the worst possible shape, well, there is no single worst possible shape, but the worst shapes would be, I would say, something like long, skinny worms. There's nothing wrong with being tall and skinny, like me. Long, skinny worms like this. These are shapes which have not much area and a lot of perimeter. All right, that makes the in that formula, the denominator will be very big, but the numerator will be not so big. All right, so those are the worst shapes. Okay, I got some examples. We have about 15 minutes, which I think is enough time to do some examples of this. Oh, I don't know if you care about this, but the isoperimetric quotient, this is what it's called in mathematics. In politics, actually, this is also called the Paulsby-Popper score, which I kind of like. It means the same thing, but isoperimetric quotient actually has been used in mathematics for a long time, but it is occasionally rediscovered by people in other fields. And apparently, this is also used, the isoperimetric quotient has also been used by paleontologists. Those are like the people who dig up dinosaur bones. And paleontologists apparently are interested in the shape of individual grains of sand or dirt when they're digging. Different dirts have different shapes to them, and one way to measure the shape, how round something is by using this isoperimetric quotient. All right, anyway, I got some examples to try, and I hope that I have the right picture here. This one. Yes. So the examples for the isoperimetric quotient are usually going to look like this. This is just a matter of convenience. You have to have a shape which you are able to find the area of, and also a shape which you can find the perimeter of. So shapes that are like this, made out of grids, are actually pretty easy to find both the area and the perimeter. So all of our examples are going to be like this. Actually, it would be hard to do those Connecticut ones because you can find the area by counting the dots, but that still doesn't tell you how to find the perimeter, which is a hard thing to do for a weird wiggly shape. But anyway, if they're on grids, this is easy enough to do. I got this on a handout, And again, I'm going to try to do the first two, and then I'll see if you guys can do the rest of them. These ones are actually, there's no real ambiguity when it comes to counting up the areas and whatever. So if you are uncomfortable with ambiguity, you will like this better than the counting the dots examples. So let's try this one on the left here first. I want to find the isoperimetric quotient of this shape, which is made up of the black squares there. So it is the area, well, it's 4 pi times the area divided by the perimeter. Really, you just need to find the area and the perimeter and then plug them into that formula. So the area would just be how many of the shaded in dots are there. I can count them up. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 23 of the squares. All right, so that's the area. That's easy enough. What about the perimeter? This is a little bit more interesting. You have to count up the distance around the outer edge here. Now, each of these squares I'm going to count as distance 1, and you have to go around the outer edge and count the distance one by one. So the way that I'm going to indicate that, you can write this however you like, but I'm going to measure around like this. I'm going around the outside edge and counting up around the edge that way. All right. So as I go around, I started over here. I go 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. I got 36. That's the distance around the outer edge. I hope that you see how I did that. That was the perimeter. All right? This is basically the work, although your final answer should be plugging these into the formula. So the isoperimetric quotient is 4 pi, come on, man, 4 pi times 23 over 36. And on the test, I would expect you to just leave your answer like that. If you're doing this on the homework, you can plug it into your calculator if you want to. Yeah?
Is it then 36?
36 squared.
And do we have to calculate that, or do we just leave it?
No.
like that?
I would say leave 36 squares like it is also. I really don't care if you know how to multiply 36 squared on your own. All right? That's the first one. Let's just try the second one here. It'll be fine. So for the area, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13 is the area. And the perimeter. You can just start anywhere and go around the outer edge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So the perimeter is 20. And so this one, the isoperimetric quotient is 4 pi times 13 over 20 squared. And that's how we do it. If you actually plug these numbers into your calculator, you can compare the isoperimetric quotient of the shape on the right versus the shape on the left. When they're just written like fractions here, it's hard to tell which one is bigger even. But if you plug those numbers in and make percentages, then you can easily compare from one to the other. All right. We have 10 minutes remaining. See if you can do the other ones here. It probably won't take you 10 minutes, but see what you think. I will walk around and make sure everybody's doing okay. I'm going to write my answers up here, see if you agree. These ones actually, you should be getting exactly the same numbers that I get. All right, I think people are doing pretty well. I see a few people still counting up the dots, but that's all right. Counting up the boxes. I had just one thing that I wanted to say before we go about this. So these were the answers that I got. The one up here, this something interesting about this one. This is area is 7 and perimeter is 16. That's what I got. I hope that you got that also. So the isoperimetric quotient is that business there. This one I actually did plug into my calculator because I think it's interesting to discuss. This is 34% if you round it off. All right. That is, according to the isoperimetric quotient, that shape there is actually not very good in the scale from 0 to 100%, right? That's actually not great, 34%. So this sort of a long, skinny rectangle here, this has IQ, around 34%. If it's the same dimensions as the one that I just did, that kind of a shape has the isoperimetric quotient about 34%. What's interesting is that shape, what about that same shape, the convex hull ratio? That would be the original area divided by the convex hull area, right? Can you say?
It's 1 because it's not a convex shape.
It's 1, yeah, because this is a convex shape already. That is to say, the convex hull is the same as the original shape. You don't have to add any extra when you do the convex hull here. So in this example, the original area, I don't care what it is. Actually, it's 7 if you believe the counting from before. These two things are equal. This equals 1. That is to say, 100%. All right. Because the original area is the same as the convex hull area here. So what's the moral of the story is just that the IQ and the convex hull ratio are two different ways to measure weirdness of shapes. Two different ways to measure how weird the shape is. Which one is better? I would say neither of them is better. They're just two different ways to measure how weird it is. If you're thinking about the context of gerrymandering, which one is better? You kind of have to think about, what if somebody did try to draw a map which had a long, skinny district, like a district maybe going horizontally straight across the state of Massachusetts or something? Is that a fair shape to use? I don't know. I mean, if you say, yeah, that's perfectly fine because it's a normal shape, it's a rectangle, then you might be thinking about it in terms of the convex hull. Whereas if you say that's long and skinny, I don't like long and skinny, you are thinking of the isoperimetric quotient. All right? I'm just saying they're just two different ways to do it. And if it comes to using these to judge a real world situation, you have to somehow judge things according to your own values about, do I like long and skinny things? All right? And I think that'll do it. This is actually the end of our discussion of gerrymandering. So after the test, we will begin something completely different, not about politics at all. See you Friday. Let me know if you want to get together to talk about test questions. I'm happy to do it. I also brought more printouts of the homework that's due tomorrow. If anybody didn't get one last time, here's some more. You can take one if you like.